Hello everyone, I am Vineeth Ravi. Today in this presentation, we are going to be presenting Docubot, a novel framework for generating financial reports using natural language interactions. We are presenting this research paper at the Content Authoring and Design Workshop at the AAAI 21 conference. This research work was undertaken by me, Vineeth Ravi, Selim Amrouni, Andrea Stefanucci, Armine Nurbakhsh, Prashant Reddy, and Manuela Veloso. In this presentation, first I'll cover some background and motivation for undertaking this research and developing this novel framework of Docubot. The main motivation for undertaking this research was to empower employees and enable them to move up the value chain. On speaking with several employees and business teams, we realized that people spend a lot of time creating and updating PowerPoint slides, business reports, and presentations rather than spending the time actually analyzing and interpreting the information and communicating or interacting with clients or business teams. And as seen on the slide shown on the screen, a study done by Deloitte found that people would actually prefer to spend the time interacting with the business and analyzing or interpreting the information in the reports rather than spending the time to create and update these presentations. This was the main motivation behind creating this framework called Docubot. In this presentation, the agenda has three main topics. First, we present the architecture and components of Docubot. Second, we show experimental results of users interacting with Docubot. Third, we present a video demonstration of a user interacting with Docubot to create financial reports. This slide shown on the screen here represents the overview of the architecture of Docubot. Docubot contains several components such as the user interface, parser, mapping engine, insights generator, knowledge base, and the document generator. We will cover each of these components in further detail in this presentation. We will start off with the user interface. The user interface is a component which enables natural language interactions between the user and Docubot. It is a two-way interaction. The user can give natural language commands or instructions to Docubot to perform various tasks which involve generating or modifying the contents of a report. The report is nothing but a digital document such as a PowerPoint slide deck, a PDF, or a Word document, and so on. Docubot can also interact with the user through the user interface to clarify any ambiguity in the user's natural language instruction. The user interface sends the input of the natural language instruction to the parser to enable Docubot to understand the intent of the user's instruction. The parser is an important component of Docubot's framework. It actually helps label and identify the several tags present in a natural language instruction given by the user. These tags help Docubot recognize objects such as pie chart, bar chart, histograms, and so on. For the parser, we use a CRF model, which is trained on 50 commonly used natural language sentences curated from users within the firm. The parser interacts with the mapping engine and knowledge base, so Docubot can ground the natural language instruction to a set of skills which Docubot can perform. The mapping engine is an important component of Docubot, which actually maps the input language to a set of structured actions which Docubot can perform. We call these structured actions as skills, and skills are nothing but the various available content creation and modification capabilities of Docubot. Broadly, we can classify skills into two types: atomic skills and macro skills. Atomic skills refer to the ability of Docubot to create or modify the content present in a single slide or a single task. Macro skills are the capability of Docubot to make changes to the entire presentation or like even 10 to 20 slides of a slide deck at a time. These could be like modifying all the title figures in a slide from red to black, or changes which affect the entire presentation or the report. The main advantage of Docubot using these skills is that it allows Docubot to save the previous instructions of the user and encapsulates them as a new object. This allows the user to acquire new skills over time and enables the reuse of these skills for future recurrent presentations. The mapping engine interacts with the user interface and knowledge base component to clarify any ambiguity in the user's intent and the Docubot's list of available skills. Now I'll hand off to Selim, who will continue with the presentation.
Thank you, Vineeth. My name is Selim Amrouni. I'm also an associate in AI research, and I'm going to present you now the insight generator part. Previously, we showed you how Docubot is able to use and normalize human input in the goal to map to concept, skills, and then to visualization. However, a presentation with only charts and visualization is not very useful. Each visualization requires a commentary that summarize or add additional content to it. This commentary is often realized based on underlying data. We refer to this natural language commentary as insight. Then, the insight generator is composed of three main parts. First, a set of primitives that are mathematical operation performed on the data. Second, the mapping from this insight to actual natural language text that is friendly to users. Finally, we need to be able to select and rank the insights in order to show only what is most interesting. For this last component, the document generator, we are showing you here how we are aggregating all the information, all the figures and all the insights into one document. For the paper, we showed using Python PPTX library to generate the presentation. We have several versions of the tool deployed here at JP Morgan, generating PDF, web pages. In this section, we will present you two experiments and discuss the Docubot knowledge base. And we will show you how employing a robust knowledge base has advantages compared to a naive knowledge base. Our first experiment is about the experiment made with naive knowledge base and real users. So just to recall, the naive knowledge base aims to learn the vocabulary employed by the users and then inferring this permanent mapping is made with the first new word learned from the first users using this new word. Our hypothesis before doing this experiment was that the number of required experiments to realize the same set of slides per different user will decrease with the number of users. For this experiment, we tasked 18 users to create 5 slides using natural language commands. What we experienced is a consistent increase in the size of the memory, and we also observed a decrease in the average number of interactions per user in order to create these slides. However, as the increase of the size is constant, decrease in number of interaction remains volatile, and this shows the limitation of this knowledge base. Based on this experiment, we decided to move on the robust knowledge base. In order to conduct a more extensive experiment with a robust knowledge base, we decided to proceed to an experiment with more than 1,000 of simulated users with varying parameters. So first, what is the robust knowledge base? In this knowledge base, we introduce the concept of belief score. It's the probability of a word belonging to the concept the user was referring to. So every time the user will interact with Docubot, Docubot will increase or decrease the belief score of a certain word. In our experiment here, we can define the matching score. So the matching score is a metric that measures if the vector of the sub-concept is true or not. So how do we simulate the user? We base the user simulation on the use of word2vec. Based on that, we can define two types of users. We have the collaborative and the non-collaborative users. In our experiment, we will vary the proportion of non-collaborative users. So for each of the experiments, it's divided in two phases. A first phase called the learning phase, the training phase, and a phase of evaluation or a test phase. So during the learning phase, the knowledge base is exposed to both collaborative and non-collaborative users. During the evaluation, the knowledge base is exposed to collaborative users only. Here are exposed the results for one of the experiments. So in this experiment, it's for the learning phase. The proportion of collaborative user is 60%. They are tasked to create 3 1,000 slides. On the x-axis, you can see the number of episodes, and on the y-axis, the evolution of the matching score. We can see here in blue the naive knowledge base, in orange the robust knowledge base. So while the robust knowledge base learn as fast as the naive knowledge base in the first phase, it will quickly plateau at a ratio that is close to alpha, while the robust knowledge base will pursue its learning and it will continue to grow. In this last slide, I'm presenting you the average of matching score between the naive and robust knowledge base for many of the parameters. What is really good here is that for all the scenario, for all the set of parameters, the robust knowledge base is consistently better. And now it's time to show you a video demonstration of a potential use case of Docubot. as a conclusion, we can say that we built a new framework that enables the automation of the creation and the modification of a recurrent document through natural language interaction on both sides. So from the user to Docubot through natural language commands to perform tasks, and from Docubot that generates natural language commentary in the form of insights in order to provide these insights to the user. Through experiments, we showed the robustness of our framework, and it has been demonstrated with real and simulated users. We are very happy and honored we presented today Docubot, and we will welcome any question, and feel free to reach out to us